Yeah, what is that? This always takes a time to appear, right? So, okay, what is happening? Oh, it is there. It is taking time to open. Yes, so in the meanwhile, again, let me rewind. Aisha, please send that question paper to in the group so that Mariam can see that. And in the meanwhile, this is not. Yeah, please start working.
Okay.
Okay, so when it will start working? Yeah, now it is. So we understood about transformers, right? And it is a device with which we can stabilize the voltages, right? So it had two kinds of construction. Let me write it again. So it is a device with which one can increase or decrease the voltage, right? Of so if we are increasing then of voltage of low current or high current. So let's say we have a low voltage of high current. So we can increase it in the high voltage and low current. And if we have high voltage, low current, then we can increase the then we can decrease the voltage and then increase the current. So this is how we. And what is the principle behind it? So principle is as Aisha said, right? One numerical in EMI. So its principle is it is based on mutual induction, right? Why mutual induction, Aisha? If I ask you why mutual induction? Yes. Why there is a mutual induction?
Because the
Yeah, because there are two coils involved, right?
yes,
So yeah, so this will induce some current in this, and this will induce some current in. So that is why. Good. So it is based on mutual induction and construction. So construction is we can do it in two ways. So one would be that we have these ends, and we so this is a soft iron core, right? And in this soft iron core, we wrap around. Okay, One moment, guys. Let's stop. Yeah, so this is a soft iron core, and the coils are right warped around this one. So this is called the primary coil, right? And this is connected to the AC supply. That is why we are calling it the primary coil. And then we have this secondary coil, and in this secondary coil, this load resistance is connected. So this is the secondary coil. So this is the construction. And we can also construct this in this manner also, that we have, so this is a soft iron core, this one, and then it is warp around like this. So this one, and this one. This is the secondary coil, and this is the primary. And this is the load resistance. This is the soft iron core, right? So when we supply a voltage, let's say when we supply a voltage EP, right? Then what will happen is that, so this will induce some EMF in this one, right? Because the current is changing. So in the secondary coil, there would be an induced EMF, and that would be equal to, let's say there are n terms, so that would be ns and d phi by dt, right? So similarly, the flux is changing, the same flux is changing. So due to the mutual induction, this will also create an EMF, and that would be equal to E, right? And this would be equal to NP d phi by dt, right? So when, let's say this is equation 1, and let's say this is equation 2, right? So if we divide these two equations, then ES by EP, this would be equal to NS by N, right? Okay. And let's say we are assuming that there is no flux leakage, right? So we are assuming no flux leakage. What do we mean by flux leakage? That there are no current which are going beyond this area, right? So all the flux are inside this one. So that is why we are calling this as no flux leakage, right? Okay. So this is what we got this condition, right? Where this ns is number of turns in secondary coil, and np is number of turns in primary coil. And if you guys have any question, then you can please ask, right? So now we are assuming that, let's say this is 100. So let's say the efficiency of this transformer is 100%. So whatever power is created in the primary coil, that is converted into the secondary coil, right? So if efficiency is 100%, right? Then power in the primary coil, this would be equal to power in the secondary coil. So this would be equal to EP, IP, right? And this would be equal to, let me write as I. Yes. So do I have any question? What is efficiency, right? So let's say you are, okay. So let's say you are given a bucket, right? And then you go and then you pour some water and then you take the water to your house, right? So let's say you would be called 100% efficient if all the water that you have carried is went to your house, right? But let's say the water is sprinkling out, and then some water is splashed out, and then you take in your home 50% of water, right? So your efficiency has been reduced. So now I am saying that efficiency is 100% means that all the power which is generated in the primary coil, this is converted into the secondary coil, right? And similarly, all the power generated into the secondary coil, this is converted into the primary coil. So this transformer is 100% efficient, right? In your 11th class also, you must have learned that what is the efficiency of the Carnot engine. So you provide some heat and some work is done. So W by Q is the efficiency, right? So that is how you calculate the efficiency. How much, so you are provided something and how much work you are doing with that. So that is called the efficiency. Understood? In this case, the power converted to the primary coil is equal to the secondary coil. That is called the 100% efficiency. Understood, Maya?
Yes, sir.
Okay. So then this would be equal to ES and I. Right. So this is another condition. Now let us, so we have two conditions. One condition is that, one condition is ES by EP. This is equal to NS by S, right? And the second condition is that EP by ES, right? EP by ES, this is equal to IS by I from here, right? So these are the two conditions that we have. And the idea of transformer was what? That we can change the high voltage low current to low voltage high current. This was the idea, right? Or vice versa. Right, guys? So now let us find out that how can we do that. So one would be, first would be the step down transformer, right? Step down transform. So remember, you are supplying the voltage with the primary coil itself, right? You are supplying the voltage in the primary coil. So all the things that we will do is we'll calculate in the primary coil and the result will show in the secondary coil, right? So because let's say this some power supply is coming and then you have built a transformer and then the output is given in the secondary coil. So that is the idea. So first one is step down transform, right? In the step down transformer, this number of turns in secondary coil, this is less than number of turns in the primary coil. That is why this is down, right? Okay. So now let us write the first condition in a different way, right? So let's write EP by ES And I was writing VP, right? So remember, this is VP. Okay. In the previous cases, I was writing VP, so just remember that this is VP. Okay. So now this is NS, right? So now if my NP is greater than NS, right? So if my NP is greater than NS, which means that this would be, right? NP is greater than NS, right? Right, guys?
Yeah.
So if the NP is greater than NS, which means that NP by NS, this would be greater than 1, correct? So I take this in this side. So this would be this. Now EP would be ES, right? So this is greater than 1. So EP would be greater than ES, right? Which means that ES is smaller than ES. So that is why we provided a higher voltage, right? But due to the transformer's action, we have got a lower voltage. So we got lower voltage, right? We got lower voltage, which means that that is why we are calling it a step down transform. Understood? Any question in that?
No.
Okay, so now what about the current? So the current was this was EP by ES. This was equal to IS by IP, right? So if we write IS by IP equal to EP by ES, so this is greater than 1. EP by ES, we have just found out that this is greater than 1, right? Which means that current in secondary coil would be greater than the primary coil. So we have changed the lower current, right? Primary current, primary coil has had the lower current, right? Low value of current. But we have changed that value to a high value. Understood? Any questions? Any questions, guys?
Mm.
Good. So now let us understand about the second one, which is a step up transform. Right. So what is a step up transformer? So in this case, NS is greater than N. Right. So what was our voltage? EP by ES, right? Or let me write it. We can write it in, right? So ES by EP, this is NS by NP, right? So our NS by NP is greater than 1, right? Because NS by NP, this is NS greater than NP. So NS by NP, this is greater than 1, right? So we put the value in here. So ES by EP, this is greater than 1. So ES would be greater than E, which means that voltage in the secondary coil is high, right? So we have changed the lower voltage to a higher voltage with the use of the transformer, right? So with the use of this number of turns in the coil, we can either So these are the number of turns, right? So with the use of this number of turns, we can either increase or decrease the voltage. So this is the transformer action. And similarly, when we look up to the current, so current was ES by EP. This was IP by IS, right? So let us write that IP by IS. This is equal to ES by EP, and ES by EP is greater than 1. So which means that IP is greater than IS, which means that IS is less than IP. So current in secondary coil is low. So any doubt up to this point, guys?
No, sir.
So please note it down. From where? Yeah, from where? Please note it down. So in your school, have they completed this electromagnetic waves?
Mhm.
Oh, they have completed. Yeah, so that will take only 2 or 3 classes, electromagnetic waves. So I will, yeah, we'll do some questions and then I'll start that electromagnetic waves.
Sir, can you please scroll down?
Yes. Yeah, whenever you guys want me to scroll down, please tell.
Mhm.
So here, this is P is power in primary coil and PS power in secondary. And remember, I have written in here in the form of peak voltages, peak voltage and peak current. But we can also write it in uh, RMS, and so this we can also write as VRMS, VPRMS, and IRMS P equal to VSRMS, right? And ISRMS. So this we can also write because these are ratios. So ratios would be equal.
Sir, can you please scroll down? Sir, can you please scroll down?
Whenever you have guys have noted it down, please tell. Yes, noted everyone.
Yes, sir.
Aisha, what about you?
Done, sir.
Good. So now this chapter is over, right? And yeah, one more important thing to note down is that yeah. So there are some losses in transformers that we should take care of, right? And the first one is that there is not an ideal condition. There would be some flux leakage, right? So there would be some flux leakage. So to prevent that, so there would be flux leakage in the transformer, right? Because all the flux will not pass through the secondary coil, right? All the flux will not pass through the secondary coil, right? Because some flux uh, it may happen that some flux will pass in this way, right? So all the flux will not pass through this secondary coil. So there can be some flux leakage, right? So to prevent that, this is the thing that we use. So we wrap around them in simultaneously, right? We overlap them. So to in this way we can reduce the flux leakage, right? So there would be flux leakage in the transformers, and to prevent that, we wrap them overlap, right? And there could be also some eddy currents, right? So due to what is this eddy current? That we have this soft iron core, right? So due to the flux, it will create some current. This this soft iron core plane. So this will create some induced current, and that will oppose this current induced in the secondary coil, right? So and then the coil or the soft iron coil will be heat up. So to prevent that, we laminate that soft iron coil, right? So due to the induced current in soft iron core, the core gets heated, right? So what do we do to prevent this? We laminate the soft iron core, right? Now there is also the resistance in the wire of coiling, right? So due to the resistance of the wiring of coil, the transformer gets heated, right? And also to prevent this, we use thick wires. Okay. And lastly, there is some hysteresis loss. So this is not in the syllabus, but earlier you guys had this hysteresis loop, right? And what was that? So let's say at equal interval, the current changes its polarity, and then the magnetization changes, right? So due to the change in magnetization, because what kind of current or voltage do we have? We have this kind of current, right? So the current is, let's say at first cycle, this is the current. So at first cycle, current is positive, but in the next cycle, the current is negative, right? So let's say that first cycle, the current is behaving like this, but in the next half cycle, the current is behaving like this, right? The current is moving in the opposite direction. So the magnetization would change, right? Because due to current, there is a magnetic field, but the current is changing its direction. So magnetic field will change its direction, right? So magnetization will change. So due to this change in magnetization, you have this hysteresis loss, right? So there is uh, hysteresis loss due to changing magnetization. Right, so these are the losses that can happen in the transform, right? So we should take care of these losses. So please note down these points, right? And if you guys have any doubt in these points, so please ask.
Done, sir.
Done.
Done, sir.
Oh, already noted. Good. Okay, so to prevent this, what do we use? So to prevent this, we use magnetic material of low hysteresis loss, right? So their magnetization doesn't change that drastically. So that kind of magnetic material use. Okay, so whenever you guys have noted it down, please tell.
Done, sir.
Done. Yes, Aisha noted.
Mhm.
Okay, so then let us do the other topic. There's some problem with charge. So now this chapter is over, and what did we learn in AC? Right. So first we started with AC generator, right? We started with AC generator and we saw that by changing the angle of the armature, we created, right? So phi was VA cos of omega t, right? And then we changed this angle and we created an EMF which was E naught and sine of omega t, right? So where this was this peak voltage and this was the sinusoidal behavior and this was the instantaneous behavior. And then what did we do is that, so where then we saw that the graph of this was this, right? So this was E naught and this was E naught sine omega t. And then what we saw that we connected this AC supply. So and after that we calculated the average EMF in the full cycle, which was what, guys? Which was what? Yes, everyone, what was this? Already forgotten. This was zero. Yes, zero. This was zero in the full cycle. And then we calculated average EMF in half cycle, right? And this was how much?
So you are the guy.
Good. So this was 2 E naught by 5. And then thirdly, we calculated the ERMS voltage, right? And what was this? Yes, guys, what was this? This was E naught by root, right? And this is the supply that we get from the powerhouse. So whenever you are hearing that 220 volt supply, so that is VRMS that you are getting, right? So always we do the calculation with the RMS values. So power would be I square, right? R, and this is the RMS. So whenever we do the calculation in the circuit, that we do with the RMS values, right? And whenever we do the phasor and all the diagrams, that we do with the peak voltage. So this we have to keep in mind. Okay. And then we calculated the two things. So then we got to know about the phasors, right? And phasors were what? So they were the sinusoidal, they behaved like a sinusoidal behavior, right? And they were rotating vectors. So let's say we had, I gave the example of a clock. So let's say this is the second needle and it is moving, right? So it is changing its position, but its length is fixed, right? So that is what we do with the phasor vectors, right? So their peak voltage, this length is peak voltage that is fixed, but their angles are changed. So so we talked about the phasor vector of voltage supply E, right? And this we represented as, so let's say this omega t is angle, right? And this E naught is the peak voltage. And when we resolve this vector in the y-axis, so then we got the instantaneous voltage. So this was the idea of the uh, phasor diagram, right? And we can rotate this vector in this angle, right? In this angle, in this angle, in this angle, in this angle. So angle can be changed, but this length, which is the peak voltage, that would be fixed, right? So after that, we understood about the average power, right? And before that, we understood about the power factor. So power factor was cos phi, and then we understood about average power, and this was VRMS, IRMS, and cos phi, right? So keeping these in mind, where phi was phase difference, right? So these are the things that we learned. And after that, what did we learn? We learned that we have, so what would be the AC current in resistive circuit? This we calculated, right? So we had this resistive circuit, and we supplied an AC voltage, right? And then we saw that what was the current in this circuit. So we calculated that E was IR, right? And we calculated I to be I naught sine. Okay. So we calculated this I to be I naught sine omega, right? Where this I naught was E naught by R. So these are the things that we calculated, right? And then we drew the phasor diagram, right? What is that? Yeah, and then we draw the phasor diagram. So phasor diagram was this one. So this was the voltage, which was this, and the angle is the same. So current angle was same. So again omega t, but current has a lower magnitude. So this was this. This was I naught, and this was equal to I naught sine omega t. And then we also drew the graph of these two. So this was voltage, right? So this is minus E naught. This is E naught, and then we draw minus I naught, and this was pi by 2 pi 3 pi by 2. So this was this, and then this, and then this, and then okay, so not this one. This is the highest value, right? So this and this one. So this was the diagram of this resistive circuit. This we understood, and then we did this Then we did this inductive circuit, and we had this inductor, and we had this supply, and then we calculated the current. So current we found out was because our E was LDI by dt. And then we calculated the current, which was, anybody remember what was the current? Yes, you guys remember what was the current? This was I naught sine omega t minus pi by 2. So the current in the inductive circuit, current was lagging behind pi by 2, right? And when we draw the phasor diagram, so this was E naught, and this was omega t, and this was I naught. And we also draw the graph, but you guys already right. And third one we did was this capacitive circuit. And in the capacitive circuit, what did we do? So we had this capacitor, and we have this supply, and then we calculated the current. Right, this has a capacitance of C. So voltage was this, and current. What was the current? Yes, this was I naught sine omega t plus pi by 2. Okay, one thing I forgot to write. So I naught was E naught by 1 by omega c, or this is x c. And in here, I naught is E naught by xl, where xl is omega l, and in here xc is 1 by omega c. So this xc and xl acts like a resistive supply, right? So they opposes the motion of current. And then we also drew the phasor diagram, right? So the phasor diagram was, this was our E naught, omega t, and 90-degree ahead. So current was 90-degree ahead, right? So this was the capacitive circuit, and then we added the all the circuit, LCR circuit, right? And we had this LCR circuit, and we calculated, so then we calculated the current. This was I naught and sine omega t plus phi, where this phi was the phase difference, right? And we calculated that this was the phasor diagram. So from the phasor diagram, we calculated the effective resistance. That was the impedance. So from phasor diagram, we calculated that this was the current, which was I naught, and in in the same phase, this was VR, and at 90 degree, so this was VL, and at 90 degree, this was VC, right? So this VC was larger, so we wrote down this as VC minus VL, and then we calculated the, right, and then let's say this is very short time. So at omega t was our V naught, right? And then we found out that V naught was root of Vc minus Vl square plus Vr square. So this was our voltage supply. Remember, whenever we have, let's say, these are the voltages, right? So let's say this is 4 volt, this is 3 volt, this is 5 volt. So in the usual circuit, what is the total voltage? In the usual circuit, you just, let's say you have this one, right? So in the usual circuit, when I ask you to calculate this voltage, and this is 435, so you just add them up. This is the total voltage, right?
Yes, sir.
Right, guys? But in this case, you cannot just add them up. You cannot. Why? Because they are not in the phase, right? They are, so this is in this phase, this is 90 degree ahead, and this is 90 degree lagging, right? So you cannot add them up in this way. These are vectors, right? So you add them in these way. They are not the vector, but they have different phases. So you add them up in this, right? Okay, so with the use of this voltage, we calculated the impedance, right? Impedance was XC minus XL square plus R square, and then we calculated the phase difference, which was XC minus XL by R, and we calculated the power factor, which was R by Z. These are the things that we calculated in the LCR circuit, right? And after that, we talked about resonance. So in the resonance, what happened that you provide the natural frequency omega naught such that your XC becomes XL. So in that case, your impedance becomes minimum, and your current becomes maximum. This was the case of the impedance. So this Z became R, and this I naught became V naught by R. So this was the idea, right, guys?
Yes, sir.
Where this where this omega naught was 1 by root LC, right? This was the idea. Okay, and yeah. So then, what else do we did? And then we learned about this transform. In transformer, we understood about step down transformer, right? And then we, in the step down transformer, turns in the secondary coil is less than primary coil. And then we learned about this step up transform. And this is NS greater than. So these are the things that we understood in the uh, current AC, right? So any doubt in this chapter? that you want me to elaborate? Yes, guys, any doubt?
No, sir.
Good. So now we will do a couple of questions. And in the next class, right, from the next class in the next week, I will start this EM wave, right? And it will take only two classes, 2 or 3 classes to complete, right? So first I will talk about displacement current and then Maxwell equation and then electromagnetic waves. And after that I will talk about the different electromagnetic waves, right? So there is a electromagnetic spectrum and what are radio waves, gamma waves, X-rays, or all these spectrum of electromagnetic waves. But before that, let us do some questions in AC current. This is seventh chapter, right? Why this is? Yeah. So now let us again do these. Yeah. So not here from the exercise question. Okay. So which one? So 7.6 is easy one, right? And 7.7 is connected to a variable frequency 200 volt AC supply when the frequency of supply gets the natural frequency. What is the average power transfer to the circuit in one complete cycle? So we have to calculate the average power at the natural frequency, right? When the frequency of the supply equals the natural frequency of the circuit. So now the frequency is omega naught. Then we have to calculate what is the average power transfer to the circuit in one complete cycle, right? So you guys please calculate that and tell me what would be the solution. But before that, let us do one simple question. Let us do this simple question. This one, 7.6. So you have a capacitor and is connected to a this 27. So this is okay. So you have this inductor. This is connect to this charged capacitor. This is charged, and then this is the inductor. So please calculate the angular frequency of free oscillations of the circuit. So remember, you have to calculate the natural frequency, and you guys already know that. Who got disconnected? Mariam, so Mariam got disconnected at the time of the question. Yeah, Aisha, you please calculate and tell me what would be the answer. So you know that, yeah. So you know that what is this is 27 millihenry, and this is 30 microfarad. So please calculate and tell me what are you getting. Oh, so you have already written the answer. 1.11 into 10 to the power 3 radian per second, right? Okay, so yeah, so we know that omega naught is 1 by root LC, right? So this is L is 27 millihenry, right? Milli is 10 to the power minus 3, and then this is capacitance is 30 and 10 to the power minus 6. So we have 639 and then this is 8. So we have 27 into 3 into 10 to the power minus of 8. And then this will come out to be 10 to the power minus 4, right? And this is 9, right? So 1 by 9 into 10 to the power 4, which is, yeah, so this is point 1 and then 1 into 10 to the power. So 1.1 into 10 to the power 3 rad per second. Good. This is what you will get, right? Okay. Now, good. So now please calculate the. So what did you get? So now please calculate this 7.7 question. Good, good, Ash. So you have to calculate the average power, right? This is VRMS. Oh, I will not write. So you please calculate and tell me the answer. Remember, whenever they have given you these things, so this is the RMS value which is given, right? This is the RMS value. These are all, so oh, the peak voltage. In here they have given peak voltage. But whenever they don't mention, so this is the RMS values that are given, right? Yeah, so whenever you get the answer, please tell. Remember, they want us to calculate at natural frequency. How many questions does this chapter has? Oh, good. So only this. R is 20 ohm, right? L is 1.5. C is 30. So this is Henry. This is 35 microfarad. And VRMS. This is 200 volt. And yeah, these are the things we have to calculate. PF. Yes, did you get the answer or any doubt, any confusion that you have?
One answer.
Yeah, please, can. Oh, so you got the answer. Impedance is 20 ohm. I got power 2000 watt. Good. So did they ask to calculate impedance? Okay, so you calculated the impedance, right? That is good. So X is C minus XL, right? And square plus R square. And but okay, so how did you calculate? Uh, how did you calculate this XC and XL, Aisha? How did you calculate that? Yes, Aisha. Yes, Aisha, how did you calculate this XC and XL? Because you need this, right? Impedance, you got 20 ohm. Oh, good. So, yes, yes. So 20, right? Good, because at natural frequency, this is 0, right? So your Z is R. That is why I thought that how did you get impedance? Yeah, so, okay, so Z would be impedance, right? And then average power would be, right? So cos phi is R by Z, right? And this would be 1, right? Because our phase difference would also be how much? XC minus XL by R, this is 0. So phi would be 0. So cos phi would be 1. So average power would be VRMS, IRMS, and then cos phi is 1. So this is V naught by root 2. This is I naught by root. And V naught by 2 and I naught would be V naught by R. Good. So then you will get, so this is, okay, RMS. So this is RMS, right? So this would be VRMS would be V naught by root 2. So V naught is root 2 VRMS, right? So root 2 VRMS and root 2 VRMS by 2 and R. So this cancels